Let's meet the very first machine learning model, and honestly, one of the most useful. It is just a straight line, but a line that learns. Say we want to guess the price of a house from one simple number, how big it is. We collect a few houses we already know. Each dot here is one house. To the right means bigger. Higher up means more expensive. Look at the shape. Bigger houses cost more. The dots climb from the bottom left to the top right. There is a pattern hiding in here, and we want to catch it. Here's the whole idea. What if one straight line could stand in for the pattern? Give me a size, and I just read the price off the line. So the model is a line, and learning means finding the right line. This first line is a lazy guess. It misses almost every dot. A better line would pass right through the middle of the cloud, like this. A line has only two knobs. The first is how steep it is. We call it W. Turn it up, and price climbs faster for every extra bit of size. The second knob is where the line starts. Its height. We call it B. Slide it up, the whole line lifts. Slide it down, it drops. That is the whole model, just two numbers, W and B. Learning is nothing more than finding the two that fit best. But what does best even mean? Look at the gaps. For each house, there is a distance between the real price, the dot, and what the line guessed. That gap is the error for that house. A good line makes these gaps small. A bad line leaves them big. So now we have something to measure and something to shrink. Here's the clever part. We do not just add the gaps. We square each one. Picture a real square sitting on each gap, its side as tall as the error. Why square them? Because a square grows fast. A small miss is a tiny tile. A big miss becomes a huge one. Squaring tells the model that large mistakes hurt much more than small ones. The best line is simply the one with the least total tile area. So the model has a job. Slide the two knobs around until that total area is as small as it can be. Think of it as a valley. Every line is a spot on the hillside, and the bottom of the valley is the best line. Watch the line settle, and watch the tiles shrink as it finds the sweet spot. When the line cannot do any better, the error stops dropping. We have reached the bottom. That line is the answer. Now the payoff. A brand new house shows up, one we have never seen. We know its size. We go up to the line, then across to the price. That is our prediction. The line turned one fact into a useful guess. Of course, size alone does not decide a price. Bedrooms matter, age matters, how far it sits from the city matters. The good news is the line barely changes. We just give every clue its own steepness knob, its own W. Each feature gets a weight that says how much it pushes the price up or down. The model still adds them all up and adds the start value B. Same simple recipe, just more knobs. And a quick honest note. If two clues live on very different scales, like size in the thousands and bedrooms in single digits, we gently rescale them first, so no single clue bullies the rest. One last warning, and it follows us through all of machine learning. If we let the model bend hard enough to touch every single training dot, it looks perfect here. But it has memorized the noise, not the real trend. On a new house, it will likely flail. The calm straight line, which misses a little here, usually predicts new houses far better. Keeping the model simple on purpose is called regularization, and it is how we stop a model from memorizing. So that is linear regression. Pick a model, a line, measure its error with squared gaps, slide the knobs downhill until the error is smallest. That exact rhythm, guess, measure, improve, is the heartbeat of every model we will build, all the way up to giant neural networks. Next, we keep the same line, but teach it to answer a different kind of question. Not how much, but which one. Yes or no. That is logistic regression.